All right, here's the notes for chapter 12. This is the green packet of homeworks. It's going to be over chemical bonding and chemical shapes. Um, to start, I want to start talking to you guys about something called valence electrons. Valence electrons, they play a fundamental role in bonding, and they're the highest energy level electrons. So basically, not all electrons are made equal. Valence electrons are the most important. They are the electrons that allow things to bond together and make like molecules and make compounds. What this means is the S block, if you remember from chapter 11, if you already did that chapter, the S block and the P block um, electrons are going to be our valence electrons, never D and F. They lag behind. What I mean by that is if you guys look at your periodic table, you would see the 4S block and the 4P block in one row, but in the same row you see the 3D. So 3D kind of lags behind 4S and 4P. So basically valence electrons are any electrons that are in the S block and in the P block. And the maximum number of valence electrons you can have, or things want, is 8. Here's what I want you guys to do. On your periodic tables, if you want to go ahead and just pause for a second and take it out, you can do that. But I'm going to add something to this picture here, and I want you guys to actually add it to your periodic tables. It'll make it a lot easier for you to remember how many valence electrons different elements have. So hopefully by now you have your periodic table out. And here's what we're going to do. We're going to add some numbers on top of the columns here to the periodic table. And not every column is going to get one. Remember I told you that the S column and the P area of the periodic table, those are the ones that are going to get these numbers, not the D section and not the F section down here. So let's start over. I'm in the hydrogen column here. And what I'm going to do is I'm going to add a number 1 right here. And what this means is that every element in this column has 1 valence electron. The next column over, the column that has beryllium in it, I'm going to put a 2. What that means is that every element in this column has 2 valence electrons. Now we're going to skip the D block section. That's all like the transitional metals. And I'm going to jump on over to the column that has boron in it. Now this column is going to get a 3 on the top. What that means is all these elements in this column have 3 valence electrons. The carbon column, that's going to get a 4. Those have 4. Nitrogen is going to get a 5. Oxygen's column is going to get a 6. Fluorine's column will get a 7. And lastly, the noble gases here, they will get an 8. Okay, so all of these have 8. One exception I'll talk about in a second is going to be helium. But like neon, argon, krypton, all of these guys here have 8. All of these guys have 7. All of these guys have 6, 5, 4, 3, and then over here 2 and 1. Now, what's the point of having 8 valence electrons? Well, I have this analogy here, and it might be a little old, I don't know, but there used to be a phrase called "I want to be like Mike," like you want to be like Michael Jordan, and they had a shoe commercial. So I want to be like Mike. Basically, what that means is noble gases, all of those argon, neon, they all have 8 valence electrons. And if you remember, I told you guys that noble gases don't like to bond; they're very snooty. So basically, all other elements that aren't noble gases want to be like the noble gases. They're going to try to manipulate themselves in order to get 8 valence electrons. And how they do that is by bonding. And that has a special name. It's called the octet rule. It's basically the observation that atoms form to be the most stable when they're surrounded by 8 valence electrons. And the only exceptions are hydrogen and helium. Hydrogen and helium are just too small of atoms that if they had 8 electrons, they would just kind of be unstable. Like they would just like throw up the electrons. They just couldn't support that many. So the maximum that hydrogen and helium, it should have helium right here as well. Hydrogen and helium only want 2, where every other element wants 8. Okay, now we're going to start talking about something called Lewis dot diagrams. And basically what that is just drawing dots around an element, and that's indicating how many valence electrons an element has. Some of you guys might have done this in another science class, and it's actually really easy. And here's my advice for it. Imagine a box around the letter, so like the symbol. Each side must get a dot before you double up on the sides. And I have an example here. Here's hydrogen. Here's my imaginary box I'm going to put around hydrogen. And what we're going to do is we're going to look at our periodic tables. We're going to find hydrogen. We're going to find out what column it's in, how many valence electrons it has. If you find it, you'll notice that hydrogen is in the column with 1 valence electron. So what I have to do is I have to represent that 1 valence electron by putting 1 dot next to H. Now I could pick any side I want to. I could go down here, I could go over to the side, I could go on top, I could go on this side. But just 1 dot for 1 valence electron. Let's do our dot on the top. And that's it. 1 dot symbolizing 1 valence electron for hydrogen. Let's try some more examples. I have phosphorus here. We're going to open up our periodic tables. We're going to find phosphorus, figure out what column it's in for the number of valence electrons it needs. If you notice, it needs 5. So what I'm going to do is I'm going to draw like an imaginary box around this P. You don't really have to draw the box, but for the first couple I will. Now I need 5 dots around this P to symbolize the 5 valence electrons. And I told you that each side has to get a dot before I can put another dot on the side. So what I have to do first is I have to go 1, 2, 3, 4. Now each side of my box has a dot. I need 1 more dot to give me the 5 valence electrons that I need. Well, I'm going to just pick a side. Let's go with the top again, and I'm going to add my 5th dot. There's the 5 valence electrons for phosphorus. Let's try oxygen next. One more time, I'm going to draw that imaginary box. I'm going to find oxygen on the periodic table. I noticed it has 6 valence electrons, therefore it must get 6 dots. Each side has to get a dot. Now I need 2 more dots. Well, I'm going to put 1 on the top. Now I need 1 more dot. I have a total of 5 so far, but I need 6. Now each side cannot have more than 2. So once a side has 2 dots, you cannot add any more to that side. So there's no more dots going on the top since it already has 2. I'm going to pick 1 more side and I'm going to add 1 more dot. Let's just go around here. Let's add it to the right side. So I'm adding my dot over here. 6 dots, no more than 2 per side. And that's oxygen's valence electrons. Again, though, you could have added those dots on any side you wanted to. You could have went like the 2 on this side, like that. This would have been just as fine. Oh, maybe I'm 1 short. Here, that would have been just as fine, adding it to this side instead of this one. All right, let's try fluorine. This time I'm not going to put the dot or the box around. I'm going to find fluorine on the periodic table. It has 7 valence electrons, 7 dots. So 1, 2, 3, 4, 5. Now this side already has 2. I can't add any more there. So here's 6. Can't add any more there. Let's go down here and make 7. Neon. Neon's a noble gas. It has 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. All sides are filled with valence electrons. Now this is what all elements want to look like. They want to have these 8 valence electrons. So like oxygen, Oxygen wants 2 more electrons. Fluorine wants 1 more electron. Phosphorus wants 3 more electrons. And that sort of ties in with their charges. If you notice, like phosphorus is in the -3 because it wants 3 more electrons to fill that octet. Fluorine is in the -1 column because it wants 1 more electron in to make its octet. Oxygen is -2. It needs 2 more to fill its octet. Okay, so that's Lewis dot diagrams, simply just drawing dots around, and that's it. All right, now last little bit of this video, I'm going to just talk about some different types of chemical bonds. Basically what a chemical bond is, it's a force or a glue that holds elements together in a molecule or a compound. Basically what happens is most elements make bonds by either transferring electrons, by gaining, losing them, or some just share their electrons. And the whole goal, again, is to get that noble gas-like electron configuration or 8 valence electrons. They want to be like Mike. They want to be like the noble gases. There are 2 kinds of bonds out there. First one we're going to talk about is ionic bonds. Ionic bonds are held together by a transfer of electrons, and ionic compounds have ionic bonds. Covalent bonds are involved with sharing electrons, and molecules or covalent compounds have covalent bonds. So that's pretty easy to remember. If you're an ionic compound, you have ionic bonds. If you're a covalent compound, you have covalent bonds. All right, let's dive into ionic bonding here. Ionic bonding happens when you have a metal element, any metal element, and a non-metal element. A transfer of electron occurs. The metal element loses the electron, and if you remember, I talked about this earlier in the year. I called it a cation. Cat ions are positive, and then the non-metal will gain the electron, and they're called anions. When this transfer of electrons occur, both atoms will have reached their octet. They'll both be surrounded by 8 valence electrons, and that's the whole reason that they're bonding together. If they already had 8, like the noble gases, they wouldn't need to bond. But since they don't, they kind of have to like manipulate the system by bonding, and it allows them to get those 8 valence electrons that they want. All right, so here's an example of sodium and chlorine, and basically what we're going to try to make, or what this would make, is good old table salt. You know, I'm making some NaCl here. Okay, if I take a look, each one of these dots is representing a valence electron, and on the outermost level for sodium, it only has 1 valence electron. On the outermost layer for chlorine, chlorine has 7. So what's going to happen is sodium is going to bump into chlorine and be like, hey, chlorine, I noticed you need 1 valence electron. I have 1 to donate. Would you mind taking this one? And chlorine's like, oh, hell yeah, I'll take that valence electron. So basically what happens is the valence electron gets donated from the sodium over to the chlorine. And I'll add my little dot here because it's been now transferred over. Chlorine now has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons surrounding it. And now that this valence electron is gone, this outermost layer no longer exists. This layer is now the most outermost layer for sodium. And if we count, it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. So both are surrounded by 8 valence electrons, by sodium giving away 1 and chlorine taking it in. These are just some other examples of compounds that would be ionic compounds. If you have a metal calcium with chlorine, it's a metal with a non-metal. Silver with NO3. So silver is a metal. NO3 is one of those polyatomics, but it's made up of nitrogen, which is not a metal, and oxygen, which is not a metal. We have barium here. Barium is a metal, fluorine non-metal. So there's zillions of ionic compounds out there. You basically can just grab any metal element you want and any non-metal element you want, jam them together and crisscross their charges, and ta-da, you have an ionic compound. There's some characteristics for ionic bonds that I want you guys to know. Oop. And the first one is, sorry about that. The first one is that they exist in something called like a crystal lattice, which basically means it's a repetitive arrangement of atoms. This is like a three-dimensional drawing of NaCl. The green dots represent the sodium, the purple ones represent the chlorine, and if you notice, it gets very repetitive. It goes like purple, green, 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 over and over and over again. It basically makes a crystal. And if you guys ever looked at salt underneath a microscope or something, this is what salt looks like. And if you kind of notice, it does look like a crystal-like pattern. And then these are some properties of ionic bonding. One is they have a very high melting point. You can feel free to look up the temperature of salt, what it would take to melt it, and it's very high. Like you could crank your oven up to your highest setting and just dump a container of salt in the oven and leave it in there for 4 years. You could come back 4 years later and that salt would still be in there and it wouldn't have been melted because it's just not high enough to actually melt down that compound. It has very high melting points. Another one is their solid or room temperature. Of course, high melting points are required to melt them, so of course they'll stay solid. They're really good conductors at when they're dissolved in like water. If you guys think like horror movies, like somebody always drops a toaster into a bathtub and they get zapped and electrocuted, right? That's because there's ions like chlorine and sodium and fluorine and a whole bunch of other things in water that cause an electrical current possible. However, if you had, and don't try this at home, but if you had a perfect scenario of like a sterile bathroom, you're in like a $1 million lab or something, and you fill up a bathtub with just pure water and you dropped your toaster in it, you would just have to buy a new toaster. You would still be alive. But again, don't try that at home because you'll never get the perfect setting. There'll still be ions somewhere in that water and in your bathtub. So again, do not drop a toaster in your bathtub. All right, the next kind that I'm going to talk to you guys about is covalent bonding. Covalent bonding occurs when two or more valence electrons get shared between two non-metal atoms. So now metals are not even involved here. It's strictly between non-metal things. There's going to be two types of covalent bonds. There's going to be one that's called nonpolar covalent bonds, and then there's going to be one called polar covalent. Nonpolar covalent bonds is when electrons get shared equally between the two atoms. So me and Mr. Brzezinski are ordering a pizza, and we get it, and we split it 4 slices and 4 slices. We shared it totally equally. We both got 4 slices. That would be like nonpolar covalent bonding. We each got 4. We equally shared it straight up perfectly. Polar covalent is an unequal sharing. Let's say me and Mr. Brzezinski again ordered that pizza, and I took 7 pieces and he only took 1. Technically, we still shared that pizza. Like, he still got a piece, but it was way, way unequal. And that's called polar covalent. So an example of that would be like when an electron is being shared, but one atom has way more control over it than the other atom does. Those are also referred to as dipoles. I'll talk a little bit more about dipoles coming up. There's going to be different types of covalent bonding as well, like the number of bonds you can have. There's things called single bonds, double bonds, and triple bonds. Now, single bonds happen when one pair of electrons get shared. One pair meaning 2 electrons get shared. There's also double bonding. double bonding is when two pairs of electrons get shared, so a total of 4. And then triple bonding is when 3 pairs of electrons get shared, or a total of 6. Covalent bonding examples, again, just like ionic, there's zillions out there. You take any two nonmetal elements, smush them together, bada bing, bada boom, you have a covalent compound. The very, very, very last thing I'm going to show you, I'm going to go over it kind of quickly at the end here, is something called electronegativity. Electronegativity is a property, and I'm actually going to define it for you on the next slide. So I'm going to kind of skip through this one, and I'm going to be right back on it. So don't freak out that I'm flying through this page. But electronegativity is the ability to pull electrons closer to an atom. So the higher electronegativity you have, the greater strength you have. The ability to pull an electron closer to you. If you think of electronegativity as a tug of war, fluorine is the top dog. Fluorine is like that jock who's like on roids and has muscles on top of muscles, on top of muscles, on top of muscles, on top of muscles. It's just like he could just pull you across the room without even trying. So fluorine can pull an electron way closer to itself than any other element can. Cesium, on the other hand, cesium's like Mr. Blue. He's got, pathetic weak arms. He can't even, pull a small child in tug of war, and it's kind of sad to watch. So they're the total opposites. Fluorine, super strong. Cesium, not so much. All right, now diving back into electronegativity and how it relates to bonding. When you have a pair of elements with a electronegativity difference of 2.1 to 4.0, that causes an ionic bond. For example, cesium 0.7, fluorine 4.0. The difference between those two numbers is 3.3. 3.3 would fall into the ionic type of bonding, and that makes sense because cesium is a metal, fluorine is a non-metal, and I told you ionic bonding happens when you have a metal element and a non-metal element. Now, when you have an electronegativity difference between 0.5 and 2.0, that's the polar covalent, the selfish sharing, the I get 7 pieces of pizza, Mr. Brzezinski gets 1 piece of pizza kind of thing. And then if you have 0.0 to 0.4, that is non-polar covalent. That would be like sharing the pizza 4 slices perfectly equal. Here are just some other examples, and you can feel free if you want to draw this chart, and I can leave you to do these bottom ones if you really want to. But here's just some quick examples. If I had H bonded next to an H, both H has an electronegativity of 2.1. The difference between those two numbers is 0. So when these two H's bond together, they have non-polar bonding, which means that they're equally sharing their electrons. They're splitting it right down the middle, like the 4 slices apiece. H with Cl, I have H again, 2.1. Cl, that's 3.0, and that's coming from this chart right here, 3.0 for chlorine. A difference between that's 0.9, and 0.9 falls into the polar category. 0.9 would fall in between this kind of a thing. So that's selfish sharing. That's like the 7 pieces to 1. And then you have hydrogen and fluorine, 2.1 and 4.0, difference of 1.9. That's even more polar. Basically what that means is the fluorine has way more control of the electrons versus the hydrogen. Even though they're still technically sharing it, fluorine is getting control of more of the electrons than the hydrogen is. And I'm not really going to talk about dipoles. I don't think they're on that paper at all. So we're actually going to stop right here. This will be enough for you guys to do the first page or the first homework page in the green packet. You can feel free to comment on the video if you have any questions, or email me or something like that. I'd be glad to help you out any more than if you need more help or something, just let me know. And that is it for this one, guys. I hope you have a good day, and I'll talk to you later.